Hi, everyone. Can you hear me well? Can you hear me well?
Yes.
네.
Okay, good. So we'll start our lecture today. So we are going to have two types of discussion today. One is some continuation of a MATLAB coding for Fresnel and Fraunhofer diffraction, or you can say the MATLAB coding for Scalar diffraction. So previously, in the last lecture, we have seen the so-called Fresnel cosine and the Fresnel sine method. And then what we are going to do today is that we are going to discuss other types of a method based upon scalar diffraction theory. So let us start. So the Fresnel and Fraunhofer approximation allow diffraction pattern calculation, and it's going to be very effective, especially for calculation of image formation and the calculation of beam propagations. And what we are going to do today is that we are still talking about rectangular aperture or slit. For the two-dimensional case, we are going to talk about rectangular aperture. For one-dimensional case, we are going to talk about slit. And then we are going to briefly review Fresnel cosine and sine method first. And then we are going to talk about Fourier method, Fourier transform method, and the convolution method. And of course, we are going to discuss some other method as well, but we will follow these contents. Okay, here is the coordinate for our discussions. So C eta is our aperture plane here. So aperture plane. And our observation plane here it is. And note that these planes are parallel to each other. So it's not tilted. That is very important assumption. So in fact, in reality, like augmented realities or virtual realities or some other complicated imaging system, this aperture plane or image plane and observation plane is not necessarily parallel to each other. And then we have to think about very complicated situations, but it is beyond our scope. So we are going to assume it is parallel to each other. So that is our simple assumption. But AR is not parallel. Okay, that's one thing we need to make sure. And we are going to review some of the basic intuitions about what we are going to talk about. So here is the certain aperture. So here's the aperture. And then it has a certain width, about 2W. And by diffraction, it is going to spread out. It is going to spread out. So we have already defined the Fresnel number. Fresnel number is a kind of a measure how we are going to describe the diffraction in terms of near field or far field. Okay, so its reference was 1, NF equal to 1, NF equal to 1. And then in addition, we have defined another beam diffraction spread B, which is lambda Z over W, lambda Z over W. If you think about this is the Z over W, Z over W, so that you can see that it is how much it is spreading, or lambda over W it is. And then if you think about it, this B is given by W over NF, W over NF, okay? So that means if NF is large, this B is small, that means it is near field. So either way, NF or E, we can guess what range we are dealing with. So NF equal to 1 is the reference. If NF is much larger than 1, then it is the near field, and then we have to follow the, as you know, the Fresnel diffraction. And then NF is much, much smaller than 1, then we have to think about Fraunhofer. Okay. And we have seen that from here to here we can actually describe how the image is formed using single scalar diffraction theory. And then in some special cases, we get the Fresnel diffraction integral, and then in some cases, Fraunhofer integral, which is basically the Fourier transform. So, so we are going to always talk about Fresnel number as a kind of measure, whether to decide whether we are going to consider the near field or far field. Just a minute. Okay, what we have learned in the previous class is that this is our scalar diffraction approximation. More specifically, this is a so-called the Fresnel diffraction approximation based upon some assumptions. We have already made some assumption here, but we think that it is valid. So this is our starting point. So this is this integration, if you look at it closely, there is our aperture, the field at the aperture. Okay. And it is integrating over the aperture plane. Okay, so it is integration over the aperture plane. And our field is that the field at the observation point. So remember that this is xy and theta, right? And then we have a so-called quadratic phase. So basically, it has a field at the aperture plane multiplied by the quadratic phase term, and then it is integrating over the aperture plane. And then we get our field at the observation point. Of course, it has a certain spherical wave propagation term here. Okay. So we have thought about Fresnel cosine and sine, and then today we are going to talk about Fourier transformation and convolution. So as a very simple examples, a square aperture over width of 2W, so that means it is so from here to here, so 2W. Okay, and it is expressed as a kind of rectangular function on C and eta. As you know, rectangular function is the 1, inside, outside is 0. And the Fresnel diffraction equation is given by this rectangular function, so that C eta is going to be both confined into Wn minus W. And then our U C eta within the aperture, it's going to be 1. Okay, so this is our reduced Fresnel integral. And then if you look at it, it is decoupled. It is decoupled. So it is function over x and function over y only. And then it is given by ix times iy. And ix is nothing but this one, this term. And iy is this term. Okay, that's what we already know. And then if we change the variable like this, and then the alpha 1, alpha 2, beta 1, beta 2 is like this. And then it is given by ix is the Fresnel cosine term like this. And then once we know this, then ix is y is known, then we just simply multiply ix times iy. And then our intensity pattern would be is multiplication of ux and uy. U times u star. Okay, complex conjugate, and then you get these factors like this. Okay, so it's 1 over. This is 1 over 4th term coming here. And that's what we have already seen. And then let's make the problem a little bit simpler so that it is, we are going to talk about slit rather than aperture. It is one-dimensional slit. So and then we are going to change the variable such as that the U1 and U2 is a scalar field aperture and the scalar field at the observation point. Because in MATLAB coding, if you have a same variable, then it is very confusing. So that we are going to set the U1 and U2 for the sake of MATLAB coding. Okay, but basically it is same form as before, right? And then if you look at it. Okay, this is the same form as this before. So here we have used the same U, and then it is going to be a little bit complicated if you do the coding. So we have to define a different variable for field at the aperture plane and the field at the observation point. That's all we need to think about. Okay, so we change the variable. U2 is our field at the observation point. U1 is the field at aperture. And the coordinate in the aperture plane is now using alpha, okay? U2, this is something strange. Sorry. I made a mistake, okay. And this is the same thing, the field at the aperture plane times quadratic phase. Quadratic phase, function over alpha minus x or the c minus x, either way. And then it is given by this term, okay, quadratic phase. And then because of it is only integral over alpha, which is the aperture plane coordinate, and then the x is independent of integral, and that is coming out, and then you can check it. It is another quadratic phase, and then we have a quadratic phase here, and then we have a linear term, because here alpha minus x is alpha minus x squared is alpha squared plus x squared minus 2 alpha x. Okay, so x square term is here. It is taken out of integral. Alpha square is here, quadratic phase, and then the linear term is shown here. So basically, we have slightly changed the expression right here. And then using normalized pupil coordinate, we can write the diffraction equation as here. This is this. And then we have this term. So this is going to be Fresnel integral. So remember that Fresnel integral was integral over this quadratic phase. And then if you look at it, this term times this one is nothing but altogether is Fourier transform. And what is going to be Fourier transformed is this term. So Fourier transform of field at the aperture plane times quadratic phase. Fourier transform of this is going to be our field at the observation point. So that we have two different viewpoints. One is the directly utilize the Fresnel integral, and the other one is using Fourier transform. But basically, it is the same. It is the same mathematical form. Okay. And of course, let's review. The Fresnel integral is defined as this, and then it is divided into Fresnel cosine and Fresnel sine. Okay. And then we have used the Fresnel in our MATLAB coding. And the MATLAB coding for the one-dimensional slit, it was you returned f and x as a slit. A is was the Fresnel number NF. Right? If you put it, and then you depending upon calculation, remember that the NF is less than 1. NF is something is wrong. And then we get this term, and then we get the complex conjugate, and its absolute magnitude is going to be our intensity. So basically, it gives you the intensity plot. So if you do the like this command with the subplot, you get the 3 subplot, and then M and F equal 10, 100, and thousands, and you can see that it is near field. Okay, so that's what we have done. So the basic idea is that you directly calculate Fresnel integral using Fresnel cosine and the planar sine. And then let's try to think about it. That's what we have done in the previous classes. And in the case of a Fourier transform, we have to think about, once again, we have a field at the observation plane times this quadratic phase, and then it's Fourier transform. Okay, Fourier transform. And then for the case of a one-dimensional slit, and then we get this expression. Okay, so that's what we have already done. The field at the aperture plane and the quadratic phase and its Fourier transformation. And note that this is the B is given by this one propagation beam width, and then we have these factors. Okay. So here we are going to think about slit. So we are going to use is rectangular function. And then, of course, quadratic face is this one. Okay. And then here is the Fourier transformation method. So we start with this function rectangular, which is the ux with the qchop function. Qchop is the already defined in the your MATLAB folder. If you look at it, there is a qchop file, and then you can just call it. And then you get this term is nothing but qchop is a rectangle. Okay. Okay. And then what you do is that anyway, and then basically you do the Fourier transformation. Okay, Fourier transformation, and then you plot it. So you have if you look at it, you can look at the folder. There is an f-slit function. Then it is calculating the diffraction by utilizing Fourier transformation. And what is being Fourier transformed? This term, so which is the u. And in the routine, I didn't say specifically that calculates the real part and the imaginary part, and at the same time intensity. Okay. So for the case of NF equal to 1, this is our function that is going to be a Fourier transform. Okay. This is what we have. And then because of a Q is the complex number, so we get the real part and the imaginary part. And black is the real part and the blue is the imaginary part. And this is our intensity pattern for NF equal to 1. So in order to plot this, you just type in f-slit comma f-slit 1, and then you get this plot. Okay. And then it's a little bit curious to check out. Thus far, we have introduced two methods. One is using Fresnel cosine and Fresnel sine. Okay, and then you get the absolute magnitude square, and that is slit. And then we get the new method, which is based upon Fourier transformation, and then that is called f-slit. So we have a f-slit and slit. So that we define the f-slit for the given NF. This is A is NF. For the given NF, we have an array over Fy, Fx, which is the field that is calculated by the Fourier transform. And then slit is calculated by the Fresnel integral. Okay. And then you just plot two variables, fx or yx, fly, fx, like this. And then you just plot together. And then you can see that for the case of NF equal to 1, it is almost identical. That means Fourier transform and Fresnel cosine and Fresnel sine is giving you very good agreement, so that you can see that you can choose either way. If you feel the Fourier transform is fine, then you can use it. But if you prefer to use the Fresnel cosine or sine, then just go for it. Okay. And then this is the MATLAB coding called compare, so that you just what you can do is that compare, and then this is the one is this NF Fresnel number. Okay, and then you get this one. And how far can you go if we vary the Fresnel number? How well those two methods agree? And in the case of a larger NF, in the case of a large INF, that means it is going to be this side. That means it is going to be near field. So when you go to the near field, then for the case of a Fourier transformation, we have a ziggle coming out. And it is mainly due to some of the problem that is called aliasing. So that means Fourier transform is working fine for the case of NF is less than 1. But in the case of a near field, Fourier transformation is not that precise because of a built-in problem. So anyhow, so Fresnel is the standard. So whatever you do, if you go to the near field or far field, Fresnel equation is Fresnel equation. So the best way to describe the propagation is a Fresnel integral, right? And then we have a built-in method, built-in function for the Fresnel cosine and Fresnel sine calculations, and then just use it. That's the one way. But if your NF is near smaller than 1, okay, smaller than 1, then Fourier transformation is much faster, actually. Fourier transform is much faster than this actual. Just think about it. In the case of a Fresnel integral, you have to compute 4 terms, right? You have to compute 1, 2, 1, 2, okay? So you have to compute 4 terms and then you do some calculations. And that's the things you have to do it. But in the case of a Fourier transformation, you define function and just Fourier transform it. So it's much faster, okay? So it depends on your choice. But the most important choice or the reference for choice is that the Fresnel number. If the Fresnel number is less than 1, then its Fourier transformation is as good as the Fresnel integral method, okay? Okay, we have to think about another method. So if you look at the one-dimensional slit case or any one-dimensional problem, then you'll find out it is actually, remember that it was exponential I times x minus alpha square, okay, was coming in. So let's look back. Okay, remember that this. So we have a c eta and x minus c, y minus c, right? So that we get this. This is nothing but convolution, right? Convolution f integral f okay. So this is what we have. So that it is basically Fresnel diffraction or scalar diffraction integral is, you can interpret 2 ways. One is you can interpret as a Fourier transform, taking out all the terms out, or you can just think that this is the convolution. Oh, this is the convolution, right? So we are going to think about convolution, okay? So basically, U2, our field at the observation point is a convolution of field at the aperture plane with the quadratic phase term. Okay. So our field at the observation point is a convolution over U1 and Q. So basically, this is our starting point, okay? And then we have a very important relationship. So if you have a convolution relationship in the real space, and then if you do the Fourier transformation, both sides, convolution in real space is now just a multiplication. In less spherical space or in K space, or vice versa. So basically, if you know what the Fourier transformation of field at aperture and the Fourier transformation of a quadratic phase, then just multiply it, okay? Then you get this relationship, okay? Fourier transformation of a convolution is multiplication. This is not x, this is multiplication. And then for the case of this quadratic phase, if you look at it, quadratic phase is this one. This is the, you can see that it is a Gaussian with a certain coefficient. And then luckily, the Fourier transformation of Gaussian is also Gaussian. Fourier transformation of Gaussian is also Gaussian. Of course, the coefficient would be changed like this, okay? So Fourier transformation is also quadratic phase, Q, okay? So that we know what the quadratic phase is. Fourier transformation of a quadratic phase is nothing but the function itself with some different coefficient, okay? So we know the Fourier transformation of our field at the observation point is multiplication of Fourier transformation of field at the aperture times the same quadratic phase that we already know, okay? And then this is the Fourier transformed one, and then if you do the inverse transformation, then you get U2x, right? And then you have to do the inverse Fourier transformation, right? And then for the known U1 and for the known Q, and you do the Fourier transformation. It's basically the same as before. Remember that we were doing the Fourier transformation for field at the aperture plane with the quadratic phase. But now in this case, we have a Fourier transform of field at observation point, and then quadratic phase, and we do the inverse Fourier transformation, okay? So this is another way to see the problem, so that this is our routine. So it's based upon convolution and the Fourier transformation, okay? That's what we are going to discuss. And then this case is, we call it n-slit, and then this is the Yeah. We first Fourier transform our U. Okay, Fourier transform it. And then Fourier transformed and the chopping is multiplied. Okay. And then we do the Fourier transformation of this thing. Of course, inverse Fourier transformation. Okay. And then we do the magnitude, absolute square. Okay. And then that's what we are doing. So in this case, it also shows the real part and the imaginary part of inverse Fourier transformed case here. Okay. And then this is the NF equal to 1 case. Okay. Looks same. And then if you just type in n slit 1 is the Fresnel number, and then you get this graph. And then it's time to think about compared to Fresnel cosine and sine. And we know that n slit is the convolution, and then inverse Fourier transformation. And then slit is that the Fresnel integral. Okay. And you just compare it, and you can see that it's almost identical. It's almost identical. Okay. So that's the thing we need to remember. And other method we have to think about is that let's go back to original convolution. Okay. So here, this case we did. If you just use the convolution itself, just to use the convolution itself, it may be you can just directly calculate the U2. Remember that you have done the homework, and in the way of doing homework, you did the one-dimensional convolution, right? One-dimensional convolution program. So other technique is that just directly use convolution. And there's a built-in MATLAB coding. That is the one method. Remember that due to and then you can just directly calculate the U2, okay? And of course, Q is the quadratic phase, so that you can just decompose into real part and the imaginary part, okay? And then you do the convolution, each of them, and then get the absolute scale for the U2, and then you can get the result, okay? That is one method, and the other method is angular spectrum method. So in fact, angular spectrum method is quite useful when you have aperture plane and it is not parallel. It's not parallel. And then you get the angular spectrum method as well. Basically, angular spectrum method is that you just decompose the aperture, the light coming from the aperture as a kind of plane waves that is propagating in different directions. And then you just collect them at the observation plane. That is the way. There are many, actually, if you look for it, angular spectrum method, there are many commercially available products for angular spectrum method. And you can find it on the web. But it is beyond our scope, so that we'll just confine our discussion to the case aperture plane and the observation plane is parallel to each other. And that is much simpler. And then what is important in our class is that you have to understand the very fundamental basics. And then it's going to be interesting to further move on to other problems, okay? So it's nearly the end. What we have learned today. What we have learned today is that the diffraction theory can be tackled in various numerical way. So numerical. Historically, start with the Fresnel cosine and sine. Okay, that is one thing. Another one was the Fourier transform. Q1, Q. Okay. And then another one is a convolution. And then we get the inverse Fourier transformation. So inverse Fourier transformation for F inverse for U1, Q. So U1 is the Fourier transformation. Okay, that is one thing. And then we have a direct convolution. Q. And we have another one is angular spectrum. And these four are mainly useful for observation plane is parallel to the aperture plane. Okay. This is what we have learned today. So this is it for the time being. And then what we are going to do next is that